Hello students, welcome to today's lecture, which is lecture number 20 on classical electrodynamics. In the last class, we have seen a complete overview about the set of four Maxwell's equations in the static condition, and then we have seen how to make a transition from the static condition to the dynamic case. That means we have seen how to involve time derivatives of the electric and magnetic fields, which means correspondingly the time derivatives of the charge densities and current densities. And therefore, we have ultimately the set of four Maxwell's equations that are going to represent the complete field in the space and time. So, which means that ultimately each one of the field is a function of space and time. That means x comma y comma z and comma t. So that is what is the conclusion. We have them, and there is more to speak about that. Therefore, I would like to explain more about the set of Maxwell's equation in the next class. I would like to explain a little more about that. But before that, I also want to make something on the gauge transformation and gauges. So the concept is quite simple, and we are going to see what is meant by gauge transformation and gauges in the field theory, and especially, of course, we are limited to the electromagnetic fields. So this is quite the concept wise. This is quite simple. So the basic idea in having what is meant by a gauge is that it is as simple as saying this particular statement. Suppose if I say that the derivative of a constant is zero, you know that, right? Derivative of a constant is zero. If it is the case, then tell me what is the constant. So that is a question. So the answer is that any constant is acceptable. That is an answer, which means that there is an arbitrariness. Any means what? It could be any number, right? So there is a kind of chaos. You don't have a particular number. So every individual can choose any number and all of them work nicely. That means for all such constants, if you take the derivative, it is zero. So the condition of the derivative being zero is satisfied by all possible numbers. And we say that determining the constant has an arbitrariness. So this is true in many places, and we are going to exploit their properties. And what is meant by gauge is as simple as fixing the number. If you say I have a derivative of some constant equal to 0 and tell me the constant means, suppose if I say that the constant is equal to 4, I'm fixing a constant 4, then we say that this is one gauge. And of course, naturally the question, I'll have to provide the reason why I am fixing the value 4. You could have chosen some other number as well, right? So the point is that whenever I am going to give a number like 4, I also have to provide a reason for that. I have a valid reason why I am choosing 4. So for this reason, I am going to choose 4 as the number and say that the derivative of 4 equal to 0, and I am going to fix the constant equal to 4. If I do that, then fixing the constant to a particular number is what is known as gauge. Okay. And similarly, another person can say that I am fixing a value which is equal to 0. Okay, why 4? Gradient, or what you call the derivative of 0 equal to 0. So I would like to choose the constant to be 0. So he may give a different reason why he is choosing 0 as his removing the arbitrariness. Removing the arbitrariness means fixing the value. So I am fixing a value 4, whereas my friend is fixing a value 0. And therefore there is a question is coming. So we can always make a transformation from the 0 case to the 4. Okay. So such kind of transformations are known as gauge transformations. So there is nothing much importance to whatever we have discussed in terms of a simple constant for the derivatives. But if you are going to consider a kind of similar situation in the case of electrodynamics, that means in the discussing, or what we say in understanding the electromagnetic fields, there are some ways of fixing these constants, and we call them by a particular name. Okay, when you fix a particular number, you call it by a particular name. So one name is Coulomb gauge. And similarly, instead of fixing to one particular value, you can instead fix to another value, and that is what is known as the Lorentz gauge. So Coulomb gauge and the Lorentz gauge are the most popular and historically very old concept in the gauge theory. And we can always make a transformation from the Coulomb gauge to the Lorentz gauge, and this is what is known as gauge transformation. So first question is that where we get the opportunity for arbitrariness. First of all, you should have the arbitrariness, and then only you say that you remove the arbitrariness by fixing the value. And then the question comes, why do you want to fix the value? Second question is, what is the value that you are going to fix? And third question is, if you are going to fix a particular value, tell me the reason for fixing that value. So this is the reason. You should provide a valid reason. No? Otherwise, why should you have only two of the gauges? You can have infinitely many gauges in principle. So we give a particular name because fixing that value has some consequences. So that is the reason. So you provide a valid reason and then say that, okay, this is the gauge. So that is the whole idea about the gauges in the electromagnetic field theory. So let me therefore go to the board and then explain. But before that, I would like to make a point here. In the yesterday's class, I was explaining something about the Helmholtz theorem in the yesterday's classwork, but I did not write down on the board. So I was just speaking, or I was just explaining the statement of the Helmholtz theorem, namely that specifying the divergence and curl of a vector field is sufficient to determine the vector itself. That is the ultimate statement, but it would be better if I can write down so that anyone is taking the proper notes for the purpose of understanding and for the examination. It is always better to take the notes so that it is comfortable. So for that purpose, I will first of all show what is the Helmholtz theorem, and once that is over, then we will discuss about the gauges. Okay, so I'll go to the board and explain now. So here is the statement about the Helmholtz theorem, and you already know what is the statement, but I am writing in a formal way and it is quite simple to understand. Now consider that there is some vector such that its divergence is 0. So there exists some vector. That is how you start with. And we also assume that there is a scalar function g, and generally all these things are three-dimensional. So that's why I would like to say that it is a function of x, y, z. Okay, it can be in any coordinate system, but at least if in Cartesian system you can understand, then it is a function of three coordinates, and therefore all of them are three-dimensional vectors. That's what it is. So suppose if you have one vector and then one scalar function, then what is the statement about the Helmholtz theorem is that this constant and the scalar function can appear on the right side of the equation in such a way that the left side of the equation is divergence and curl. So you always, the point is that the divergence of some vector function and curl of that same vector function, they are given by your starting values c and g. So if you are going to have a situation like this, okay, if you are going to have such a situation, then what is the consequence? Ultimately, what is the statement is, ultimately the field, or we say that the vector field f, we say it's vector function or vector field, whatever it is, the vector f can be uniquely determined. That is the meaning, but there is an underlying condition is there for the determination of the unique f. One condition is that the vector field should approach 0 at far away distances, because x, y, z is there. So that represents the distance. If you want to know the distance in terms of spherical polar coordinate, then you consider square root of x square plus y square plus z square, that is r. We say that radially away from the origin. So that is the meaning of r tends to infinity here. So r is nothing but square root of x square plus y square plus z square. In fact, so what is the conclusion is that can you find a vector field capital F? Can you find it, provided I know what is divergence and what is curl? I know means what? You already have something in your hand. What is already there with your hand is you have the scalar function g, which is available with you, and you also have a vector valued function capital C vector. These two things are available. What is not available is f vector is not available. Can you find? That is the question. Answer is yes, it is possible to find. Okay, provided that the f vector itself approaches 0 at far away distances. And of course, this will happen only when the known function c approaches 0. So this thing will naturally happen. So when f is approaching 0, then c also naturally approaches 0 as r tends to infinity. So this is completely mathematical, and we don't invoke any physical vector here. And in our electrodynamics case, we will be considering the electric field and magnetic field. And you see that the set of two equations that are written here can be written down, one for the electric field and one for the magnetic field. So you have the divergence of electric field, curl of the electric field is specified. So when I'm saying that it is specified, now you ask the question, what is this g? The scalar function g is nothing but rho by epsilon naught. So this is a scalar function. Rho is a function of x comma y comma z. Of course, it's a function of time also in the what do you call the dynamic situation. But anyway, rho is a function of x, y, z, and epsilon naught is a constant. So everything is a scalar function. So that means g is a known function to you. It's already known to you. And coming to the c vector equal to 0 vector. If this 0 is there, the meaning is that it is 0 vector. So what do you mean by 0 vector? It is 0 into ax unit vector plus 0 into ay unit vector, etc. So each one of the component is 0. So literally speaking, we have to put a vector here, 0 vector. So therefore, c vector is actually 0 vector for the electric field under the electrostatic conditions. So based on the Helmholtz theorem, we make a straightforward conclusion that given the divergence and curl, we can uniquely determine the electric field itself. So that is the conclusion that we are going to gain from the Helmholtz theorem. And once again, you can apply the same idea to the magnetic field, where you already know that the divergence of B equal to 0, which means that the function g is equal to 0, which is a scalar. And then the c vector that you have, c vector is equal to mu naught into j vector. These things are known to you in the sense that we are only applying the current. We are only having the charge density. So consequence of that only we have this. So therefore, the right hand side quantities are known quantities, and that is what we say let c is such a quantity and g is another quantity. Okay, so when these things are true, it is possible to uniquely determine, that is ultimately the statement is that we can uniquely determine the vector valued functions, namely that we can determine E and B. So this is the point about the Helmholtz theorem that I was explaining in the last class also. But however, without writing any of these things, I simply explained over some 5 minutes time. So I thought it would be better that you have a properly something is written, so that it is more comfortable for you to understand. So let us therefore move further to the today's topic, namely the gauge transformation and gauges. So for that, what you do is, as I already explained, consider some simple situation like integral of x times dx. Okay, y is not required, only x times dx let us consider. So you know that the integral of the x ds is x square by 2 plus c comes into picture. And the reason why c is there is because d by dx of whatever quantity that you have, x square divided by 2 plus c, that goes to the original quantity x. So you are providing the reason, okay, why you are adding the constant there. That is because the d by dx of the constant is equal to 0. So this is quite trivial to you, and therefore our conclusion based on this particular statement is that there is some kind of arbitrariness, and we call the arbitrariness the freedom. Okay, when you say arbitrariness, we say that there is a freedom in choosing the constant. So it is only a different style of telling the same thing. So either you say that we have the freedom in choosing the constant. That is one way of English sentence. The other way of the English sentence is there is an arbitrariness in the determination of the constant. These two styles of saying, they all mean the same. So you understand what is the meaning here. So here I am using the word freedom. So ultimately we have the freedom in choosing the constant while still maintaining the derivative of the entire expression is equal to the original expression. Original expression in the sense that whatever you started here. So that is the idea. So therefore, what is the what is that you can do about the constant c? So that is what I would like to write down as a conclusion here. So I'll write down the conclusion. What is that I would like to write is that fixing the constant, if you are going to fix the constant, then that is what we are going to give the name gauge. So fixing the constant is what is known as a gauge. That's a conclusion. So this is how you understand. So now the concept of the gauge is quite simple. And similarly, this is one thing what I'm trying to say is that there is a word constant is to be noted. So the question is whether it is always a constant or can it be a variable also. So that is the question. So in order to demonstrate that variable is also possible, let us consider another simple integral. Let us say integral of something like x times y dx. So here it is clear what you understand from this integral is the integral is with respect to the x only, which means that the integration is partial, okay, only with respect to x. So that means y will be treated as constant. You know that y is a variable, but because the integration is partially with respect to x, y can be treated as a constant and therefore it can come out. So what happens because of this reason is that in our discussion of the previous case, we have a constant c, and now we are going to say that it is not necessary to be a constant, but rather it can go to a variable also. So that is what we are going to see. So let us therefore write down completely. So the evaluation is this. As you can see clearly, that instead of putting a constant here, we can always add any function of y, because the integration is only with respect to x. Y is treated as a constant, and therefore any function of y will remain as a constant for partial derivative. So that is the meaning. So since you have done partial integration here, the partial derivative will become 0. So if you write like this, then things are clear. And therefore what is the consequence is that ultimately the partial derivative of f of y is always 0. So there is a freedom now. Okay, what is the freedom means? You have freedom. So what freedom is there means, what is the function f of y? It is up to you. You can choose f of y as e to the power y, or you can choose f of y as cos of y. Anything is okay, right? Dou by dou x is 0. So you have the freedom to choose any function of y. And now you understand that now it is no longer a constant. That is a point to be noted. So therefore we will write down the conclusion. The conclusion is that fixing the function, whatever it is f of y, is therefore a gauge now. So ultimately, when you are fixing something, it is not necessarily a constant. It can be a function also. So that's all about it. And once this is clear, let us go to the electrostatics case now. So in the case of the electrostatics, what you have already is that you have the curl of the electric field is 0 in the case of electrostatics. And the rule of the vector calculus says that the curl of the gradient is always 0. So this is from pure mathematics, and where the phi can be any kind of a scalar function. Okay, that means it's not a constant. Scalar function means it's a function of x comma y comma z. Just to refresh your memory that we are talking about three-dimensional always. So gradient of the curl is always equal to 0. So always is very important for any scalar function that we are going to choose. This is one rule from the vector calculus. There is another rule from the vector calculus is that the derivative of a constant is 0. So it clearly indicates that the derivative is three-dimensional. So there is nothing stopping you from considering dou by dou x in the I direction, dou by dou y in the y direction, etc. So you can have a combination of all derivatives in all three directions. That is what is the del operator, right? The gradient operator. So the gradient operator of a constant, now this is not a function. So the gradient operator on a constant is 0. So there are two rules are there in vector calculus, and we have one result from the electrostatics. So we would like to combine these things. Okay, if you are combining, then what we can write. So as you can see that del is there, cross is there. So E must be equal to gradient of phi. So this is the first conclusion you can write. The second conclusion is gradient of phi is okay, but gradient of C is also 0, right? Therefore what happens is 0 can be added here. As long as you add 0 to this, Nothing happens to the original equation, and therefore why to write only gradient of phi? Instead of that, you write down gradient of phi plus gradient of c, because gradient of c is anyway 0. I'm adding 0 only here. So that is how the conclusion. Now that is what we mean to say. So let us write down whatever I explained now. So therefore electric field can be written down as the gradient of the phi. Not only that, you can also add gradient of the c, which is nothing but adding 0. So this means that the electric field can be written down as the gradient of course minus is optional. We can write down you have gradient of phi plus c. So this is quite clear from this. The minus is completely coming from the convention, not from mathematics. Of course, mathematically speaking, whether you put a minus here, okay, you can put a minus here or plus here, always 0 is there. So that will not trouble anyway. It is your choice whether to fix a plus here or minus here. And you already know that minus we are going to fix because we consider the electric potential at infinity is equal to 0. Okay, because of that reason, minus comes into picture. So that is the story about the electrostatic potential, and therefore purely for the reasons of conventions. Convention means what? Convention means where do you want to fix the 0 of the potential? That is a question. And by convention, we fix infinity is the place where the potential is 0. So that is the reason why minus enters into picture. So that's all fine. Then once you have the gradient here and the gradient here, the gradient is common, then I'll be getting a phi plus c. Here I would like to write explicitly x comma y comma z because it is a function, and c is a constant. Okay, and once you understand that, no need to write the bracket of x comma y comma z. So therefore we ultimately write down like this, and therefore remember that the phi is actually a function of x comma y comma z. Naturally it's a scalar function, okay, not a vector, and c is actually any constant. So once this is clear, now you tell where is the freedom, where is the arbitrariness. Freedom means arbitrariness. So let us therefore write down where is the freedom now. So if you are going to choose or if you are going to fix a particular constant c, because c is the constant, there is the freedom, okay, then it is known as a gauge. So what is the clear is where is the freedom means there is a constant looking there or appearing there, and therefore you have the freedom of putting any constant there. So in an English sentence we can say that electric field has an arbitrariness to the extent of additive constant. Arbitrariness, that is the any value, to the extent of, to what extent you have the freedom is you can always add, here it is clear, you can always add a constant here, that is electrostatic potential. Okay, when you write electric field, there are two ways of telling like this. Electric field has the arbitrariness to the extent of a gradient of a scalar. This is the option. That is one way to tell. The other way to tell is, if you are talking in terms of potential, I can say that electric potential has an arbitrariness to the extent of additive constant. So when you are talking about potential, gradient is not required. Okay, so if you are talking about electric field, you have to tell gradient of constant. That's all about it. So if you have that kind of a freedom, or you have that kind of an arbitrariness, and we want to remove the arbitrariness. Removing the arbitrariness means fixing that particular constant. If you fix it to a particular value, whatever be the value, you are going to fix to a particular value, then we say that is a gauge. Okay, that's all. So that is a conclusion that we have from this kind of situation. Okay, so now that we have seen the case for the electrostatics, we will now see for the case of the magnetic field. So what is known about the magnetic field is that the divergence of the magnetic field is 0 always. Okay, whether it is static case or the dynamic case, you always have the divergence of B equal to 0. This is a result from a physical result for a physical quantity magnetic field. And vector calculus says that divergence of curl of any vector is 0. Divergence of curl of any vector is 0. Because there is a divergence here, we are choosing this property. So if you want to write down that, it looks like this. It is a divergence of, that is del dot of, curl of, that is del cross of any vector A is equal to 0. So the point is that capital A vector is any vector, mathematically speaking. For every vector capital A, this result is true. And therefore, what happens if you are going to combine the result of the 1 and the 2? So let us consider some number 1 and 2. So try to apply the rule 2, or we say equation 2, to the equation number 1. Then what could be the capital A vector? So we are going to give the name capital A vector by the name magnetic vector potential. Of course, this is quite familiar to you. We have seen the details in the last class. So I would like to therefore mention the point about the magnetic vector potential because of this reason. In fact, you already know that we are able to write down the magnetic field as a curl of a vector potential. We have seen that in the last class, or even before last class. So now we are going to exploit more about this information. Namely, there is involvement of the gauge there, or there is a freedom associated. So that is the point that we are going to explore. So when you are writing mathematically, A can be, for every vector this relation is true. And if you want to apply this particular equation to our physical situation, then our conclusion is that there is a del dot, there is a del dot, and therefore this particular B vector should be equal to del cross A. So that is our conclusion. B can be written down as equal to del cross A. And in our physical situation, we will call the vector capital A as the magnetic vector potential. So that is a conclusion. And of course, the reason why we should use the potential, you don't have a proper reason, in the sense that it doesn't represent any potential energy. So there is a point to be noted. Magnetic vector potential, it does not represent potential energy. Okay, but it is just given the name historically. Historically, in the sense, when you are coming from all the way from mechanics, thermodynamics, etc. And then we have the electrostatics, and then only we are coming here. So historically, when you are coming like this, we have the habit of giving the name potential. So do you remember in mechanics, how do you define? In the case of the mechanics, you have the gravitational potential, and if you are going to take the gradient of the gravitational potential, then it is known as the gravitational force. Now in that particular case, the potential itself is the potential energy, gravitational potential energy. Okay, so the word potential is given because it represents potential energy in mechanics. So that is the one reason. Second reason is, when you are coming to the case of the electrostatics, you have E equal to minus gradient of scalar potential, and even in that particular case, we treat them, even though it doesn't have the dimension of energy. Remember, what is the dimension for the scalar potential in electrostatics? It is the volt, isn't it? Volt is the dimension for the electrostatic potential. But even then, we consider, or we treat as equivalent to potential energy in electrostatic system. And in the case of the thermodynamics, of course, you already know that we have several of the potential, like Gibbs potential, Helmholtz potential, or we say that the internal energy. All these things are considered as potential, and basically all of them have directly the dimensions of energy. Internal energy, dimensions of energy. Gibbs potential, it is actually, Gibbs potential is what? It is directly having the dimensions of energy. So the potential is generally having the dimensions of energy, particularly they represent potential energy, and therefore historically the word potential has been given whenever gradient of something is coming. And it is only for that historical reason now also we are giving the name a vector potential, that because its vector is there, that's all about it. But however, unfortunately, this particular potential is not the potential energy. This is the point to be noted. Okay, once that is clear, now we will write down the conclusion. What is the conclusion? Comparing del dot and del dot, we have the capital B vector is equal to del cross A. That is the conclusion. So you write down that. So now once you have B equal to del cross A, now we are now seeing some kind of freedom. So where is the freedom? You see, take the case of the vector calculus rule, which says that the curl of the gradient is always 0. We are considering this rule now because there is a curl here. Okay, so we have to choose a particular rule which is fitting to our equation. So right now the equation to be considered is equation number 3. So in the equation number 3 we have curl. That is why we are choosing this particular expression. So we always choose a particular expression where 0 is there always. These kind of relations are true all the time. That means the curl of the gradient of a scalar is always 0. So that is the reason. And if you want to apply this particular equation, then how it looks like. So curl is del cross, gradient is like this, you write down, that is gradient of phi. And once you have these two things, you can compare. And you can see that by comparison, del cross is there, del cross is there. And then A can be equal to the gradient of the phi. But remember that it is not only gradient of the phi, but also you can add something else, like a constant you can always add. So keep that in mind. Not this is valid for any scalar function. It is valid for any scalar function. That point you should remember. And once this is clear, we are ready to apply this vector calculus rule to the magnetic potential. So let us write down. If we apply the vector calculus rule to the magnetic field case, we can write down that the B vector can be equal to del cross of A plus gradient of G. Del cross of A, then you have a plus gradient of G. So are you able to feel this particular expression? So gradient, if you are going to expand this, I will be writing gradient of A plus, not gradient of A. How do you read? This is del cross, right? So you have to read correctly. Curl of. So how do you read this? This is curl of A. Then you have a plus the curl of the gradient of G. So two quantities are coming. Now read this. Curl of A is there. So first term is fine. And what is the second term? Curl of the gradient of G. So that is there here. Curl of the gradient of G. But this is always 0. Which means that actually I am adding a 0 to the original vector potential. That is the meaning. So you can always add 0 and say that my original magnetic field did not change. So that is the reason. So what is the comparison between the equation number 3 and the new equation is that the magnetic field is identically same magnetic field. Magnetic field did not change. But even without changing the magnetic field, I am able to have the freedom of adding gradient of a scalar function. You have the freedom of adding any gradient of the scalar function because ultimately I'll be getting 0 if I take the curl. So curl, if I apply to that, 0 will come. So therefore now you are understanding where is the freedom involved in the determination of the magnetic vector potential. So this is the conclusion. So let us therefore write down that the quantity A plus gradient of G is what we call the new magnetic vector potential. So where is the old magnetic potential then? So this is the new one, A plus gradient of G. This will be my newly generated magnetic vector potential. But where is the old magnetic potential? A. This A is the, originally I have A only. Now I added to A the quantity gradient of G. So that means as long as you have the freedom of taking any scalar function, how many such additions you can do? You have an infinitely many possibilities of adding different values of the gradient of scalar function. And therefore you can generate infinitely many magnetic vector potential. But the point to be noted is that for all such magnetic vector potential, the original magnetic field will not change. So that is the important point. The original magnetic field is not at all changing, remember, right? Because this quantity is 0, right? Essentially I am adding 0 only to the magnetic vector potential, and therefore you have the arbitrariness, or what we call, you have the freedom. So that is the conclusion. So we will write down now what is the conclusion from this. Let us give equation number 5. Okay, so let us try to understand the meaning of equation number 5 now. What is the meaning of equation number 5? Now to understand equation number 5, you have to compare the equation number 3. Okay, so by comparison, what is equation number 3? Just remember, because we came down. So remember what is equation 3? Curl of A. That is the one. So note down that and let us do that. So now we are going to compare this with equation number 3. What is that we understand? So we understand that the same magnetic field B, the word same is very important. Okay, same magnetic field B can be represented by, so whatever I explained, I try to write down in some kind of English sentence. That's all about it. okay, can be represented by infinitely many magnetic vector potentials. That's what I explained. So, and for your reference, I would like to write down the equation number 3 here. Okay, so equation number 3 is quite simple, right? B equal to del cross A. That is the equation 3. So now we compare both of them, and this is the conclusion. And now the question is that what is the reason for infinitely many? Where from the how do you know means it is because you see the G is any scalar. So because you have the word any scalar, I have infinite options are there for the scalar function. That is the reason why I have infinitely many magnetic vector potential. Okay, so all that thing is clear. So now I can write down therefore that I would like to write like this. I am trying to write down with the new and the old terminology. You see the word new here. So that means if A itself is known as the old value for the magnetic potential, then the new value is given by the old value plus gradient of G. So that is what we have been discussing. So I would like to write down that point. So A new equal to A old plus gradient of the G. So this is clear that the new magnetic vector potential equal to old magnetic vector potential plus the gradient of any scalar function. And such a kind of vector potential when generated, all of them will represent identically same magnetic field. So here same is there, identically same magnetic field. So this is the conclusion. We will still write down that. So in this way what happens? So in this way actually we can generate, in this way we can generate quite a many vector magnetic potentials for a particular given B vector. That is the conclusion. So that is what we mean to say. So this means that we will say that this means that the magnetic vector potential has some kind of an arbitrariness. Okay, it has an arbitrariness to the extent of gradient of scalar, to the extent of gradient of a scalar function. Of course, when I write scalar, you have to understand that it's a scalar function. Scalar means not a constant. Okay, if it is constant, we have to write down constant. Scalar means scalar function. So this is the one of the main conclusion that we have, which means that we now understand where from the freedom or where is the arbitrariness coming into picture. So ultimately, whether it is electric field or whether it is magnetic field, whatever be the case, we understand that some kind of arbitrariness is there in the determination of the potential, whether it is scalar potential for electric case or vector potential for magnetic case or whatever be the reason. You understand that there is an arbitrariness in the determination of the potential. So this is the main moral of the story, whatever we have done. And therefore we therefore ask the question, can you remove the arbitrariness by fixing in some particular fashion? You fix something so that you remove the arbitrariness. So that is the question that we ask. And for that, let us now do a very small calculation. You can therefore understand how we are going to fix the arbitrariness. So for that, you consider as usual, the same equation. Whatever equation I have written, same thing I am now writing once again. Only thing is that this looks much comfortable because I am not writing old and new. The old is what I am trying to keep A naught. If A naught is the old vector magnetic potential, then A will be called the new potential. So you understand that new, old, this kind of thing, no need to write. No, it is very clear. So therefore, if it is the situation, let us see what happens if you take the divergence. So let us now, we understand like this, new and old. So no need to write new, no need to write old. Okay, so what is that we want to do is that let us take the divergence of this equation. So if you take the divergence, what will happen? So the divergence of the A vector will be equal to the divergence of, open a bracket, A naught plus, you have the gradient of the scalar function. So always remember that gradient of this scalar is actually a scalar function, which means I try to say that it's a function of x, y, z always in 3 dimension. And you should know the gradient of, okay, let us simplify and then take the vector rule. plus, now you have the divergence, that is the del square operator. So now the point is that this is the divergence of A naught is that is written here. The question is, what is del dot of gradient? So del dot is divergence. This is gradient. So what is divergence of gradient? That is called the Laplacian. So if you can keep a note of that it is the divergence of the gradient. I will write down that divergence of gradient is what is known as the Laplacian, represented by del square operator. Of course, del square is a scalar operator, and you can operate it on a vector, you can operate it on scalar, both are possible. So now g is a scalar function. So del square itself is a scalar operator. This scalar operator can operate on a scalar, or it also has the ability to operate on a vector valued function. Both are possible, and now we have the scalar valued function. Okay, that's all about it. And once this is clear, as usual, you know what is A naught and what is A. As far as physics is considered, both A naught and A will represent identically the same magnetic field. So I would like to write down that both of them will represent the same magnetic field. And therefore, now we have to think carefully. So therefore, what can you say about the divergence of A? So what can you say? That is a question. In general, we can say that it may not be equal to 0. So this is something that you'll have to think. So what is that we are trying to write here is that this is the expression that you have. So this expression is there, that's fine. And A naught is going to represent same magnetic field. A is also going to represent same magnetic field. So that is fine. Now you have this equation. Only using this particular equation, what can you say about divergence of A naught? Do you believe that there is any chance for the divergence of A naught going to 0? That's the question. In general, you don't have any reason. Why should it go to 0, isn't it? Most probably, you don't have any reason for divergence of A naught going to 0. And therefore, we try to say that more generally, in most general situation, there is no evidence that the divergence of A naught can go to 0. That is what we mean to say, and we can still understand by comparing this with the original magnetic field. So probably I will write down that you consider the original magnetic field B equal to del cross A naught. It is not only that. Okay, it is not only that, but also the same B vector is also del cross A, isn't it? That's what I am talking about. A represents magnetic field, means A naught also represent identically same magnetic field, not a different magnetic field. So this is the point that you'll have to note down. And because of this reason, you don't have any evidence to expect that the divergence is 0. So I would like to write down that. Let us keep some number for comparison. So what happens is that if you are going to compare this with the equation number 1 that I am showing, then what is the point that you can write is that you don't have any reason to say that divergence of A naught is 0. Okay, so whatever I explained, I try to write here. Ultimately, what we try to mean is that we don't know the value of the divergence of A naught. That's what ultimately. Now, since we don't know, we also try to say that it may not be 0. That's all. So it is only a different way of saying that we don't know what is the divergence of A naught. Okay, so therefore, once we have this kind of information, then let us again consider the above equation. Above equation means, okay, equation A. So let us again write down that, then we'll ask the question what happens. So equation A is what you are going to rewrite once again. So what is equation A? You have the divergence of A equal to divergence of A naught plus the del square operator operating on the some kind of scalar function, And in this equation, our conclusion or our interpretation is that we are going to assume that the divergence of A naught may not be equal to 0, which means basically we don't know what is its value. Okay, that's what we mean to say, and that is one point. And always remember that G is any scalar function. That any I am emphasizing because of the arbitrariness coming into picture. Okay, so therefore the word any I frequently write down in order to mean that we have a lot of freedom in choosing whatever G we like. We have a lot of freedom to choose. So let us now exploit the freedom. Okay, what way we are going to make use of exploiting means what we are trying to make use of this freedom in a particular way. In what way we are going to choose is in such a way that the divergence of the A naught is exactly equal to the negative of the del square of G. So you need to understand what is the meaning of this. You see this, you already know about this. Okay, we have been seeing this equation, and what we know about the divergence of A naught is it is not equal to 0. Okay, that's fine. Now since this is not equal to 0, this one you have a freedom, you have infinitely many freedom. So what is the idea is that why don't you choose the del square G is exactly equal to the negative of the divergence of A naught? Then what will happen? So this is the idea that you are getting. If you are going to make use of the freedom of G means you choose any value for G, that freedom is there. Okay, so what are you making? What are you going to? How are you going to, exploit the freedom, or how are you going to make use of that freedom in order to simplify your mathematics? How we are going to exploit means choose the value of the G such that the del square G is equal to the negative of the divergence of A naught. Then what happens? Then these two things, when you add up, it goes to 0, right? When it goes to 0, ultimately we have divergence of A equal to 0. And that equation is going to be much simpler equation. So which means that I am trying to simplify the mathematics, okay, by making use of the freedom. Ultimately, that is the point. So let me write down that so that the whole story will be clear. Okay, so the meaning you write down, then it will be clear. This means that we would be able to find the function G such that del square G is such that the del square G is exactly the negative of the divergence of A naught. So the purpose is therefore clear. The purpose is that the right hand side is going to 0. That is the reason. And the right hand side going to 0 means what? Our mathematics is becoming simple. Okay, so keep a note of this particular equation A always. That is exactly we have copied. And therefore, the equation A will become simple if you use equation B. Okay, once all these things are clear, then what is the conclusion? If all these things are successful, then ultimately we have a simplified equation, namely the divergence of A right hand side goes to 0, isn't it? Then what happens? The right hand side equal to 0 means divergence of A equal to 0. So this is what I have been explaining, that ultimately we have this expression. So now you see that the equation number A has become a much simple equation. You see, this is the much simple equation where the entire right hand side has become 0. Now how it has become 0 is because you have the freedom of choosing the G in such a way that del square of the G is equal to the negative of the divergence of A naught. That is what is this. That means if you are able to this point is there, if the equation B is successful, that means if you are able to successfully find out the scalar function G such that this particular condition is satisfied, then our equation for the divergence of A has been simplified to a great extent. Solving the equation divergence of A equal to 0 is much easier than solving this kind of an equation. You'll have to realize that solving this equation is not a simple thing. You have a del square operator, second order differential is there. So in the right hand side total is 0 now. So therefore you can at least understand what we are doing. Ultimately what we are trying to do is that we would like to make the equations to a much simpler situation while trying to maintain our original physics. What is that we are going to maintain means the magnetic field remains identically same. Whatever mathematics that we are doing till now, nothing happened to the original magnetic field. Same magnetic field is there even now. But however, the equation A has been reduced to a much simple equation, and we will call this by equation C. So ultimately, you understand what happens here. This kind of gymnastics that we are doing ultimately led to a simplified mathematics. So let me therefore write down the conclusion. So the conclusion is that the physics did not change. So I will write down like this: for a given magnetic field B vector, we found the magnetic vector potential capital A vector in such a way that the divergence of the A is 0. So this is what ultimately happened. Whatever gymnastics that you did, we have ultimately, this is the conclusion. This is what happened. And now we are going to give the name because arbitrariness is now removed. Therefore, equation number C is what is known as the Coulomb gauge. Now, why it is called the gauge means we have fixed, arbitrariness is gone. We have removed the arbitrariness, or we have fixed the arbitrariness in the determination of A. Okay, so equation C is known as, if you want, you can write down, it is known as the Coulomb gauge. So now you understand what is a gauge here. So gauge means removing the arbitrariness into the picture. So now the arbitrariness is gone. Once you fix that divergence of A equal to 0, which means that A is particular. It is fixed. A is also fixed. If del dot A is 0 means A itself is fixed, and therefore now there is no more arbitrariness in A, capital A. So for such a capital A, if you take its curl, curl of the capital A, that will give you the magnetic field, which is nothing but your original magnetic field that you started. So that is the point to be noted, that we did not change the physics, namely the original magnetic field, but will still play with our mathematics, to understand the magnetic field in terms of a magnetic vector potential. So that is the entire story. That is all the story is, and therefore we will write down. Ultimately, what we are doing is that we are actually working in the Coulomb gauge. So what is the meaning of working in the Coulomb gauge means? Once you fix the divergence of A equal to 0 and then understand the magnetic field, then we say that we are actually working in the Coulomb gauge. Working means theoretically we are working. So working in the sense, whatever mathematical steps that you are doing, that is the working. Okay, it is not that we are doing any experiment with the A. There is no experiment with capital A. Okay, so it's all the mathematical calculation based on the vector calculus, ultimately to understand the original magnetic field. So if we are going to fix the divergence of A equal to 0 and then try to understand the magnetic field, then we say that we are working in the Coulomb gauge. So that is a technical language. So that's what exactly I have written here. So it's all fine. So what happens? So finally, okay, if del dot A equal to 0, so what happens is, let us see what is the important consequence. So there is a consequence there. So I'll write down what is the consequence of having the divergence of A equal to 0. Okay, so now that we have discovered the capital A, our conclusion is that we still have the original divergence of B equal to 0, and not only that, curl of the B equal to mu naught into J. So these equations are still valid. Nothing happened because of the capital A. Okay, that is what we say, that we maintain our physics intact while doing all this gymnastics. And therefore, now let us see that we are going to use once again the vector calculus rule. Okay, what we know is that we have magnetic field is curl of A, and not only that, let us substitute that. What is the curl of the B? So we have something like Ampere's law, right? That's why we'll calculate del cross B. So del cross A. Okay, so now you expand it using the vector calculus rule. You already know that, so I'll simply write down. So you read like this: curl of the curl is equal to the gradient of the divergence minus the Laplacian. So let us write down how it looks like. Del cross B is equal to the del cross of del cross A. Now apply the curl. So we have the gradient of the divergence minus the Laplacian. And now comes the Coulomb gauge. So you know now what is Coulomb gauge. There is a del dot A. So that del dot A is what we have been discussing for a long time now. And now we will use the Coulomb gauge. So if you are going to use the Coulomb gauge, what is the meaning? The meaning is del dot A is 0. That is the meaning of saying Coulomb gauge. And therefore the previous equation becomes simple now. So del cross B equal to one term goes to 0, right? So therefore we have a negative of the, so that first term goes to 0. That is what I am trying to say. Under the Coulomb gauge, then only the second term is left out. Then I have a negative of the Laplacian of the capital A vector. So that is the equation that you have. And what is your Ampere's law? And what is your Ampere's law is that you have del cross B equal to mu naught into J. So now compare these two. So if you compare these two equations, what is the conclusion? You have the del square A equal to minus of the mu naught of J, and that's all. So this is the conclusion. So that means after doing all these things, how are you going to understand the physics is like this? Because this is the equation that ultimately you have. Now this equation, if you know something from the, of course you know it, if you compare this with the electrostatic case, this is what is known as a Poisson equation. Poisson equation is what? The Laplacian operating on something should be equal to right hand side non-zero value. If the right hand side is 0, then it is known as Laplace equation. If the right hand side is non-zero, it is Poisson equation. So basically this is nothing but it's a Poisson equation, but this is a there is a vector quantity is there, therefore this is known as vector Poisson equation. So I would like to write down that. So this is nothing but this is the Poisson equation only, but in the vector form. So of course there is no difference between vector form or scalar form. Vector form means what? It is equivalent to 3 scalar Poisson equation. That's all about it. You write down the components, right? If you write down the A x component here, then the J also x component. Then we have the very standard scalar Poisson equation. How many such equations are there? 3 scalar Poisson equation is identically same as a 1 vector Poisson equation. That's all about it. So therefore this particular vector form is nothing but it is equivalent to 3 scalar Poisson equation, where the scalars are actually x component, y component, z component. And for the comparison, or you already know it, but just for comparison, I would like to write down how the scalar Poisson equation looks like for electrostatics. So how it looks like, it's a del square of the scalar potential, or the electrostatic potential is negative of the charge density by rho naught. This you already know from long back, okay? And therefore now you can compare that these two equations are looking same or looking similar. So for electrostatic potential you have a single equation. For magnetic potential you have 3 equations. This is the conclusion. Okay, so what is the main conclusion ultimately? Why did we do all this Coulomb gauge, etc.? Is that the Coulomb gauge has helped you to determine the magnetic vector potential in the form of a Poisson equation. So why do you want to reduce it to a Poisson equation? Is because when you have the Poisson equation, you know the solution methodology. Well, what is the solution methodology? Means green function method. If you did not use the, so this is very important, if you did not use the Coulomb gauge, you don't have an equation as simple as Poisson equation. It will be a much more complicated equation whose solution you do not know, or you don't have any analytical solution for that complicated equation for capital A. So the story of the Coulomb gauge, you should now understand that the purpose of the Coulomb gauge itself is that the differential equation for the magnetic vector potential has come down to the Poisson equation case, and we are quite happy because the solution to the Poisson equation is known known in the sense we know how to solve it using the method of Green function, which means that the capital A vector can be determined. If the capital A vector can be determined means you can always take its curl and say that the magnetic field is also determined. So therefore, ultimately we try to say that we are able to understand the magnetic field due to the current density in terms of magnetic vector potential. This is the mathematical foundation in the understanding of the magnetic field. Okay, so this is the conclusion. So with this I will stop for the today's class. And of course, as I already explained, in the next class I'll explain more about the 4 Maxwell's equations, and anyway that we will see in the next class. Okay.